Welcome back, everyone. Let's begin with discussion of the parabolas. Now, the literal meaning of parabola meaning throw in besides. That's what it means. Now, why would Apollonius call it that? I'm not sure, and exactly what he had in mind, but that's what it means. We're just going to call it a parabola. Okay, now the formal definition, and by the way, here's how the parabola could be generated. Remember, they have a flat surface, a plane that intersects either the upper or lower, not both, of a double nap cone in such an angle that it creates this parabolic figure. Now, we have studied, by the way, parabolas earlier, way back when we did the algebra portion of this course. But here it is again. And the parabolas that we study in this section could be either horizontal or vertical parabolas. So what is a formal definition of a parabola? I'm looking at the definition here right out of your book. So a parabola is a collection of all points, or we say the locus of all points P, and on a plane that are the same distance d from a fixed point F, which is known as the focus of the parabola. Okay, so here's how that means. Well, if you look at, for example, here's a point on this parabola, okay? And this is a fixed point F, which we call the focus. This distance is exactly the same distance as from the point to a line behind the vertex called directrix. Okay, so if we can find a set of points that satisfy this condition, then they will be on this parabola. Now, for instance, let's say I have a point, I don't know, here. Suppose I have a point here. Well, the distance from that point to this focus and distance, direct distance, that is, from this point to directrix. Notice, these are not the same distances. So that is not based on given directrix and focus in this diagram. That point was not on the parabola. So all the points here do satisfy that condition. So for example, if we look at this point, the distance from this point to F is the same distance as the point to directrix. Okay, so that's just the formal definition. But the formal definition will actually be the basis for deriving the equation of the parabola. And this is all the starting point. The distance from P to F is the same as distance from P, the point, to directrix. And remember, F here is what we call the focus of the parabola. Also, if you recall, parabolas have axis of symmetry that runs through the vertex. So I have this axis of symmetry, which we now call transverse axis. Now, just so you're aware, all conic sections have directrix and they have transverse axis. This includes the ellipse and the hyperbola. It's just their location depends on the conic section where they are. Now, let's actually derive the equation for the parabola. Now, coming to this, by the way, remember we know the polynomial form ax squared plus bx plus c. We're aware of that form. Remember, these will give us vertical axis of symmetry parabolas that look like that. If A is positive, if A is negative. Again, this we've done way back when we talked about parabolas or polynomial functions. Also, for the ones that are horizontal, we have this form of a parabola. For these, the parabola either opens to the right or opens to the left. If A is positive, it opens to the right. If A is negative, it opens to the left. Okay, so we have those already. We're going to look at what we call the directrix form, of the parabola. So here's our starting point. Again, by definition of parabola, suppose I have a fixed point F here, and this is, I'm letting the vertex be for simplicity at the origin 0, 0, but we can adjust this for parabolas whose vertex is not at the origin later on. And this is my point P. Okay, that's what this point P is. So the distance from P, and this is D, the directrix, And I try to do my best, try to make those two distances the same or equal. So we know that for a fact the distance from F to P is the same as distance from, let's say, P to Q. And I'm going to call this point Q. Okay, the coordinates of P, we're going to keep the general coordinates X, Y. Okay, now the coordinates of the focus, this is going to be X is 0, and the Y distance is going to be A. Okay, so this distance is A, and I'm assuming A is positive here, by the way. So if this distance from the vertex to focus is A, then the distance below it is going to be negative A, correct? To the rectrix. So I can label the coordinates of Q as X and Y minus A, correct? That's from here to down here, this distance. All right, and so we have these points. Now we can actually proceed. Now I'm going to use the distance formula. Okay, the distance from F focus to point P on the parabola is going to be X minus 0. That's going to be first component minus first component of the focus, quantity squared, plus we subtract the y's, which is y minus a squared, and then we take the square root of that, equal. Now for distance from P to Q, well, they have the same x, so x minus x squared plus y minus a squared, square root of. Now, when we take the square root of the right side, by the way, remember x minus x squared, that's 0. And here we just simply get square root of a squared, correct? And let's see. Okay. And hold on, let me correct this a little bit. Okay, I see what I did wrong right in here. So sorry. I went in and actually in here I had the distance from point to point. I just want coordinate of this point. The coordinate of this point is going to be x and negative a. I'm sure some of you caught that. I just didn't. All right, now let me adjust it. So the distance now is going to be what? Y minus a quantity squared. Okay, now that's better. Again, the coordinate of point P, the y component is y, the y component of point Q is just negative a. All right, now in parentheses I get y plus a squared right up here, and then I'm taking the square root of that. So when we take the square root of that, we get absolute value of y plus a. Now let's square both sides of this equation, and when we square we get x squared. The y minus a squared on the left side becomes y squared, negative twice first by second, plus second one squared. And squaring, we lose the square roots on both sides, right? And because we're squaring the absolute value, we simply get y plus a on the right side. Correct? Again, we squared both sides. Now, let's take a look at this one. Can we cancel anything? Hold on. There, this is what I'm doing. I'm squaring this, so I get y squared plus 2ay plus a squared. There. Now we can cross out y squared on either side. We can cancel a squared on either side, and let's see. So I have x squared, and let's move 2ay to the other side. Combines with this 2ay, because they're like terms now, gives me 4ay. And there you go. We have the equation of the parabola that is whose vertex is at 0, 0. Okay. Now, if a is positive, again, if a is positive, the parabola opens upwards. And if a is negative, the parabola opens downwards. Good. And we can actually solve, if we solve this for y, we get the familiar, divide both sides by 4a. See, we get this form, the polynomial form, if we solve for it. Okay. Now, one other thing about the parabola here, the line segment, there is a line segment that runs through the focus. It's the chord of a parabola. Remember, a chord on a curve or a graph connects 2 points on the curve or on the graph of the equation or the relation or the function. So if I look at a chord that runs through, I didn't mean to get rid of the y-axis, the chord that runs through the focus right in here, that is the chord connecting 2 points on the parabola. That chord is called latus rectum. Latus rectum. And the literal meaning of this, well, this is from Latin, right? So this Latin for the word lattice in Latin means side, and rectum in Latin means straight. Okay, so the literal meaning of latus rectum means a straight side. Okay. Now, sometimes we're interested in finding the equation for the latus rectum of a parabola. Now, for the parabolas, by the way, that open to the sides, the equation, this is, we call them the sideways parabolas. So if the parabola opens to the right, or if it opens to the left, these have equations. Y squared is equal to 4ax. All right. And again, this one has a vertex at 0, 0. What if the vertex is not at 0, 0? Well, we can use translation of these parabolas. So for example, suppose I have one that's like this. I can move it to the right h units and move it up k units. Now it's at hk. You know, we've done that before. And we get a parabola whose vertex is no longer at 0, 0. Okay, so using translation of functions, which we talked about extensively when we did the algebra portion of the course, we can actually now write the HK form of this. The HK form. Again, the form that we're looking at, it's called the directrix form. The directrix form of the parabola. So what is the HK form? The general form, directrix form, is going to be x, and I'm going to use minus here just to emphasize the subtraction symbol there, x minus h squared, and equals 4a, and it would be y minus k squared. And h and k are exactly like before. The vertex is at hk. All right. So this is, oh, sorry, there's no square on that. So sorry. And there you have it. That would be the directrix form for parabolas whose vertex is not necessarily at 0, 0. And then for the sideways parabolas, the form becomes y minus k, and this one now is squared, and then 4a x minus h, and that one is not squared. Okay, this one again, the vertex is at hk. So we adjust for what you call it. We adjust for these in the formula, the equation that we write. Okay, and we'll look at some examples real quick in a moment here. One last thing is that all of these conic sections that we discuss have reflexive property. So for example, the reflexive property of a parabola is the following, which is used in design of satellite dishes, to say the least, and many other applications. Let's say you have incoming rays from a distance. These could be radio waves. They reflect to the focus. So it doesn't matter where they hit the surface, they all collect. It can come in this way and it will go right there. It can come in this way, it will go right there. So that's why with design of these satellite dishes, usually there is a receiver right in here, right? I don't know the technical name, an LLD, LMD, something like that. Or they place it right where the focal point is, right here, and they attach it to the body of that. There you go, to the satellite dish, and that would be the reflexive property of the parabola. Any ray, incoming ray that hits the surface, the inside surface, not outside, inside, will collect at the focal point F. All right, so let's take a look at just maybe a few examples here and see how we're going to work this. So in my first example, let's say I want to find the equation of a parabola. Okay, there you go. Find equation of parabola. And suppose I'm given the focus to be at -2, 0. And the directrix, remember, directrix is a line. It's not part of the graph. It's just an identifying line that helps us find the equation for the parabola. And suppose the directrix has equation x equal 2, because it's a line, I gotta have an equation, right? If it's a vertical line, it's x equal 2. A horizontal line would be y equal 2. All right, and remember, directrix is always behind the vertex. Focus is always in front of the focus vertex. Focus in front of vertex, directrix behind the vertex. All right, now suppose we're given this piece of information and we want to find the equation, and then we find 2 points that define the lattice rectum also. All right, now here's how I start this, by the way. First, I'm going to do a rough sketch. Doesn't have to be precise or too exact, as long as it's realistic. So focus is at -2, 0. So this would be the focal point. F is at -2, 0. The fact that focus is to the left, that means the vertex is going to be right here. And directrix, by the way, is at x equal 2, right? Vertex is always halfway between focus and directrix. This is line x equal 2. And because focus is in front, I know the parabola is not going to go like that, because that one will have a focus here, right? Not in front. So that means the only way that this can go is like so, correct? So this would be the parabola. Now, because it's opening to the left, I know that A is negative, right? A is less than 0. And what is A? A is the distance from vertex to focus. A is -2. And all I need to do is recall, because this is a horizontal parabola, the equation is going to be y squared 4ax, vertex at 0, 0. And just plug in for A. A is -2, so that will mean the equation is y squared equal -8x. And again, this would be in the form that we leave it. We don't need to solve for x. Oh, there you go. We're good enough. We could solve for x, but we're going to leave it like that. Okay. Now we want 2 points. 2 points on the chord, the lattice rectum. Sorry. The 2 points. This is the lattice rectum, so it would be a point up here and a point down here. Well, these points are collinear, right? The points on either side of the lattice rectum and the focus. So that means if they're vertical and collinear, means they have the same x values, correct? So all points going to have x is -2. So how are we going to find this? Well, if x is equal to -2, then we can plug in y squared is equal negative 8 times negative 2, and that gives me 16. Y must be plus or minus 4. So this point, because it's in the third quadrant, right, this point is going to be negative 2 and negative 4. Both x, y will be negative. And this other point, the one on top, this one, sorry, I'm going above, outside of the example, this is going to be at negative 2 and 4. So the answer to 2 points that define the lattice rectum would be negative 2, 4, and negative 2, negative 4. And the transverse axis, by the way, the transverse axis in this case is going to be the x-axis. The transverse axis for horizontal parabolas, if the vertex is at 0, 0, transverse axis is the x-axis. If the parabola is somewhere else, if the parabola, for example, is up here, this is the transverse axis, right? The transverse axis runs parallel to the x-axis. Okay, parallel to the x-axis. We can find the equation of it easily because it's a line through the vertex. So we will have that if we need to. And there you have it. So not too bad. Let's take a look at another example. Okay, in my next example, let's say I want to find the equation of a parabola whose vertex is at negative 1, negative 2. It's not at 0, 0. And the focus is at 0, negative 2. Okay, now what I do, which really helps me, I will graph or plot points based on what's given, the information that's given. I'll try to plot the points and then decide how this parabola going to go. Is it going to be horizontal? Is it going to be vertical? And whatever that might be. So here's my coordinate system, the xy. This one has a vertex that's at negative 1, and negative 2. So I'm just going to try to, there you go. Maybe this is there. And negative 1, negative 2. Let's go, this is negative 1, and this would be negative 2. Right in here. So that's the vertex. And then the focus is at 0, negative 2. So the vertex is actually on the y-axis, right? Right in here. That's the focus. The vertex and focus. Well, remember, focus is in front of the vertex always. Therefore, I know my parabola cannot go like that, because then the focus will be behind it. Therefore, I'm going to make it point like this. It's going to open to the right. The fact that it opens to the right tells me A is positive. And it also identifies the correct form of the equation of the parabola is y minus k squared equals 4a x minus h. See, all of that I get from just plotting 2 points. Now, because I'm close to, I know that this parabola is going to cross the y-axis. The question is it going to cross it here, here, here? How is it going to cross? At what point? So I need to find the x-intercepts. I'm sorry, the y-intercepts. The x-intercept for this one doesn't matter. Let's do the y-intercepts. And the y-intercept, that's when x is 0. Now, the vertex is negative 1, negative 2. I'm just going to plug into our formula, negative of negative 1 squared. Okay, is negative 2, sorry, that's negative 2 squared equals 4a. A we don't have yet, right? Well, a, I can actually find it. Remember, a is the distance from vertex to focus. This is a equals negative 1. So we have a also. Negative 1 x minus h, which is negative 1 also. Let's tidy up this thing. We get y plus 2 squared is equal to negative 4 times x plus 1. Okay. And oh, the parabola opens to the right. A, we said, is positive. Sorry, A is 1 because it goes to the right. And therefore, A is 1. We did mention A is positive right up here. All right, so there's the equation. It's 4 times x plus 1. And now I can find the y-intercept. Let x be 0 in this. I get y plus 2 squared is equal to 4 times 0 plus 1, which is just 4. Square the left side. Y squared plus 4y plus 4 equal 4. Subtract 4 from both sides and we get y squared plus 4y is 0. Now if I factor the y, I get y times y plus 4 equals 0. Correct? And then by 0 factor property, we know that either y is 0 or y plus 4 is 0. Okay. And from this, well, y is 0. We got 1 already. The other y-intercept is at -4. There you go. So I'm going to make this parabola go through there and right through here. Okay, that's the other portion, and that is a very acceptable graph of this parabola. Cool. And we found the key points. Now, that's all we wanted to find. We want to find the equation and graph this. Now, also for this one, let's locate the directrix on the graph. Remember, the directrix falls behind the vertex. It's the same distance from vertex to focus as it is vertex to directrix. So that means I need to go 1 unit behind. That puts me at -2. And I can draw this vertical line. And that is D, the directrix of this parabola. Again, it's not part of the graph. It's just more of a reference of an axis. X equal -2. Notice the directrix in this case is perpendicular to the transverse axis. What is the transverse axis? There you go. This is the transverse axis. And in this case, transverse axis is parallel to the x-axis. If you want the equation of it, it's going to be y equal, because it's a horizontal line, and it goes through point -2, right, on the y-axis. So it's y equal -2. That's its equation. And we have that. Now let's find 2 points at the endpoints of the lattice rectum for this one. Again, this would be, let me actually use a highlighter. There, that is the lattice rectum, right? The highlighted segment. 2 points. Well, I have one already. So I'm going to go points on the lattice rectum. In this case is going to be 0, 0. That's the one that runs through the origin, right? Has to go through the focus and connect 2 points. So one is 0, 0, and the other point is right here, and 0, -4. There you have it. Okay, so another good example of this one. And let's do one more for this next one. In my next example, let's say we want to get the following. Suppose we want to find the following, everything we want to know about the parabola. Find the vertex. What else? Focus, directrix, and what else? Let's do lattice rectum, and let's do transverse axis. Transverse axis. Okay, now the transverse axis, we do it at the end when we have a complete graph. Now, and suppose the, oops, sorry, I'm not sure what happened here. Okay, Let's say you're given the following equation. Let's say my equation is y squared negative 4y plus 4x plus 4 equals 0. In other words, I have the polynomial form, not the directrix form. Okay, so how do we go from polynomial to directrix form? Well, to do that, because directrix form, if you remember, is y minus k squared equal 4ax minus h. So it's in the form of a binomial on y in this case. That means I need to complete the square in y. So I'm going to group my y together and move the other stuff, the other two terms, to the right side. And then what am I going to add on the left side? Because I'm going to complete the square, right? When I complete the square, if you recall from way back when, the way to do this is to make sure the coefficient in front of the square is 1, which it is here. That has to be a must. If not, you got to make it, usually divide by the coefficient if it's not 1. But in this case it is, so the formula is you do 1/2 of the coefficient on y in this case, and don't forget to square it. So half of negative 4 is negative 2, you square it, it becomes 4. So I'm going to add 4 on the left, and I'm going to add 4 on the right side. Okay. Now the 4 on the right and negative 4, that comes in handy, they add to 0. On the left, I can write it as a square of a binomial, y minus 2 squared. And on the right, I just have negative 4x. And that looks precisely like the directrix form that we're looking for. Okay, and now I can identify, if you want, I can do this. I can write it as x minus 0 so that I have exactly the h, and this is the k. So the vertex is at hk. And in this specific exercise or example, the vertex is going to be at 0 and 2. So we found one of the things we wanted to find. Vertex 0, 2. Now let's actually graph what we know so far. And there's x and there's y. Vertex is at 0, 2, so it's right up here. Now a in this case, what is a? Well, for a, I'm matching this against the coefficient. We know that 4a is negative 4, therefore a must be negative 1. Less than 0, so the parabola opens to the left, correct? And remember, the distance from a vertex to focus is what a is in this case. A is negative 1, so we go left negative 1 and draw this. Let me make it a little more to scale. There you go. I want it not, if I do to scale, it has to be here. It's too close, so I'm just extending it a little bit out. In other words, my scale on the x and y are not the same. There. See? Okay, and it's going to open to the left, and this is going to be the focus. So we can answer the questions now. Vertex we found, 0, 2. Where's the focus? Well, the focus is going to be at negative 1 and 2. And therefore, the parabola is going to open to the left. And again, where is it going to cross the x-axis? We need to wait for that. Let's find the x-intercept in this one. Because I need to know, is it going to go this way, this way, this way? Where is it going to go? So my x-intercepts, that's when y is 0. So in my equation, I'm going to put y minus 2 squared equals negative 4x. Remember, my equation is up here. In that equation, I'm going to let y be 0, so I get negative 2 squared equal negative 4x. So x would be negative 2 squared is 4. Divide both sides by negative 4, I get negative 1. there. My x-intercept is going to be at negative 1, 0. There's only one of them. And right in here, there. That's how it's going to cross that part. And there is my parabola. Where is the directrix? The directrix is behind the vertex, same distance as A. So if distance is, let's say, 1, okay, I know it's negative 1 because it's to the left. I'm looking at the absolute value of that. So I go 1 unit to the right, and that's going to be the directrix. Directrix, its equation is going to be x equals 1. So we have the equation for the directrix. Therefore, we know the vertex, focus, directrix. We got vertex, focus, directrix. So all we need is transverse axis and latus rectum. Now the transverse axis, because the parabola opens to the side, it's going to be horizontal, parallel to the x-axis. This is your TA, transverse axis. Parallel to the x-axis, its equation is y equal to the point where it crosses the y-axis. It's a horizontal line, so it has to be y equal to a constant. And there we have that one. There's my transverse axis. Now all we got to do is the latus rectum. And the latus rectum connects 2 points. The chord of the parabola that runs, through the focus. Call this P and this one Q. All right, so how do we find P and Q for the latus rectum? Well, we know P and Q will have the same X as F, right? Let's try to find the latus rectums, or the points on latus rectum. That's a singular word. Okay, latus rectum. So that's when x is negative 1, right? Right in here. See, focus has coordinates x negative 1. So I'm going to plug in negative 1 into the equation of that parabola. The equation is y minus 2 squared equals negative 4 times x. X is negative 1, makes it 4. Let's square the left side. Plus 4 equal 4, right? Subtract 4 from both sides, and let's factor the left side. We get y times y minus 4 equals 0. And one solution is y0 by 0 factor property. The other y minus 4 is 0, which means y is 4. And there we have it. That would be this one, P. So the coordinates of point P, the higher point is x negative 1, y 4. Q, the other point, would be negative 1, 0. And we have the 2 points on latus rectum. There you go. That's a complete exercise. Okay, so maybe I'll finish this with an application. So let me grab a problem from the book, and we'll work that one. Let's take a look at this example, our final and last example. In this example, we're given a mirror. A mirror is shaped like a paraboloid of revolution. What is a paraboloid of revolution, by the way? Anytime you revolve or rotate a parabola, let's say I have a parabola here. You revolve it about this axis of symmetry, or transverse axis, means the same thing. If we rotate it about this axis of symmetry, the resulting solid, it's called paraboloid of a revolution. The revolution here is the rotation they're talking about. So there you go. You get this paraboloid of revolution. Now, clearly this would be the axis of the parabola, right? The vertical axis. The x-axis is here. The vertex is at 0, 0, the origin. And so that's how I'm going to label this. And what else? It's used to concentrate the rays of the sun at its focus. creating a heat source. If the mirror is 20 inches across at its opening and 6 inches deep, where will the heat source be concentrated? Remember, the concentration will be at the focus because incoming rays will reflect at the focus. So this is probably where the heat source right there, that's where the focus is, F. That's what we want to find out. But before we can find the focus, we need to find the equation, right, of this parabola. And where is the parabola here? Well, right in here, that's portion of it, and there's the other part of it. So that's the parabola. The coordinates of this point, by symmetry, it's 20 inch wide, so I can say that this point is 10 inches to the right, and the other point will be 10 inches to the left, for a total of 20 inches, a span of 20 inches. Therefore, the coordinates of this point is going to be 10, 6. And the other point, if you need it, is going to be negative 10, 6. Right? All right, good enough for us to do this. Because the vertex is at 0, 0, and it is a vertical, a vertical parabola. The equation is going to be in this form. I'm writing the general form, but h is 0, and so is k, because vertex is at 0, 0. Therefore, the equation of this parabola is going to be x squared equals 4ay, right? The simple version. Now, we're given points on the parabola at 10, 6, because I need to define a. Once I know a, I have the equation. And we're given a point 10, 6, so I'm just going to use that point. When x is 10, I get 10 squared is equal to 4a times y is 6. So from this, a is going to be 100 divided by 24. Okay, which reduces to 25/6. Now 25/6 is approximately about 4.17 inches in this case. And remember, a is distance. A, the distance from vertex to focus. And this is what a is. And we just answered the question that they wanted, right? So the answer is going to be what? 4.17 inches from the base along the axis of symmetry, not the x-axis, along the axis of symmetry. Because the focus is always on the axis of symmetry or transverse axis. And there's the answer, right? And then make sure, where will the heat source be concentrated? Yeah, it's going to be concentrated at focus. If you want the coordinates of focus, it's going to be 0 and 25/6 exact value, approximately 4.17 inches from the base along the axis of symmetry. All right, we're good. We're golden. We're done with this section. So hopefully everything reads fine and you were able to follow the lecture okay. And with that, we are done with parabolas. The next lecture, I'm going to talk about the ellipses. Thank you for watching, everyone, and hope to have you in another video, another lecture.